Hey, my God, what's the problem? Nah. No. Oh, why? What's the problem? Streamnet. We. Oh, แล้วทำไมมีสองอันมันซีมแล้วมาแล้ว and I don't understand why this one doesn't. Okay, no problem. Just yeah. So I zoom. Nitrino. Andพระภาวิทย์มาแล้วนะครับพระภาวิทย์ณภัทรก็มาแล้ว moment โอเคขอเทสเสียงนิดนึงนะครับเทส 1 2 3 อัครวัตรก็มาครับทำไมเสียงเครื่องนี้ไม่ออกเทส 1 2 3กระเพื่อมTest 1 2 3 oh my god there's no sound at all oh connect the wrong internet I think yes we have to use MTMax and zoom yes MTMax and which what is that that's the student upgrade your channel okay this one too OBSNo1 anyway, we have to send the file to iPad. Okay, we send the file to iPad just using AirDrop and nuclear physics to iPad. Yes, iPad. Yes, that time. To yes, this one same. Okay, andเครื่องนี้ไม่ได้ยินอีกแล้ว Host about okay. Test 1. Oh. Okay. Test 1 2 3 Test 1 2 3ครับโอเคเสียงมาแล้วwe go to GoodNote and import the file. Chapter 7. Oh, where is that? Oh, here. Okay. This one. It's M604. And today is 04. Okay, good morning everybody. Welcome you to SCI33206. I'm not sure where did we live last time. '26 lecture.มีคนไหนจำได้ไหมครับเราถึงไหนกันเอ่ยhere right this is how we control right nuclear fission we will start the nuclear fusion, right? Okay, nuclear fusion. Okay, here. Okay, we have finished the nuclear fission in, I think it's correct, right? Yeah. Okay, we will start the next topic, which is nuclear fusion. It is another kind of nuclear reaction. It's in the opposite way to nuclear fission because in nuclear fission we decompose the big nuclei into smaller nuclei, right? 0402, this one. Okay. Somewhere here. Okay. We arrive at this topic when then we will go to the second part of this chapter, which is particle physics, and the M605 has already reached several things in particle physics. Okay. Nuclear fusion is in the opposite way to the nuclear fission, because they try to build up a bigger nuclei from the smaller nuclei, and the process for nuclear fusion is the following. When two or more light or small nuclei combine to form a heavier nucleus, the process is called nuclear fusion. Okay, it's a little bit, the name is a little bit different. เดี๋ยวดูครับใช้สิทธิ์จะเข้าไหมนะใช้สิทธิ์ไม่ค่ะ Oh, I'm sorry, I didn't share the screen. Right. Okay. Okay, nuclear fusion, right? Usually the mass of the final nucleus is less than the sum of the masses of the original nuclei, because we have beta nuclei with a greater binding energy, so that's great. The next thing is usually the mass of the final nucleus is we have better binding energy per nuclei per nucleon, so the new nuclei will be more stable, and because of the mass that is less than the original one, so there will be remaining energy, remaining kinetic energy too. And there is a loss of mass accompanied by the release of energy. That's what I have mentioned in terms of kinetic energy. 3 examples of energy liberating fusion reaction are in the following sequence. Through protons, when proton is denoted by 11p, okay, 1 nucleon and 1 proton, right? Or actually it is a nucleus of hydrogen combined to form a deuteron. Deuteron is a heavier version, heavier isotope of the hydrogen, the typical hydrogen. It has 1 more neutron. A positron, which is denoted by E01, it has no nucleon, because it's the antiparticle to electron. It has number 1 because it has the same positive charge as the proton, okay, which is opposite to electron. Or it can be denoted by beta, okay, as you like. And next one is electron neutrino. Okay, electron neutrino denoted by nu E00. Okay, something like that. According to this equation, proton combine or collide another proton, we get deuteron and positron and electron neutrino. Okay, actually this one has the conservation of electron-lepton number. Yes, once we want to calculate or find the we want to find the energy remaining for all these 3 particles, we could start from the mass on the left hand side, okay, subtracted by all the masses on the right hand side at the output after the reaction, after the fusion process. Okay, on the left hand side we have two times the mass of the proton, right, or the nucleus of hydrogen 1 and on the right hand side we have mass of deuteron and mass of positron, which is equal to the mass of electron. We neglect the mass of electron neutrino, but actually it is not zero at all. Okay, once you substitute it in terms of atomic mass, you need to you multiply with 931.5, you get 0.9315. The proton will annihilate with an electron in the surrounding to form two gamma rays. So yeah, we get we repeat this equation again, and but we have one more input, which is electron, and finally the positron will disappear because it got the positron and the electron will generate the photon, okay, the gamma ray. And yeah, in this expression we could also find the remaining kinetic energy for all these two particles, and the energy remaining will be 1.9. okay, you substitute again the mass of the proton, mass of electron, and mass of deuteron. Okay, we neglect the mass of electron neutrino, and you will get the energy 1.9543. okay, a proton and a deuteron. In the second step of this route, especially on the sun, we have the light isotope of helium, which is helium-32. Okay, we start from proton, deuteron. Okay, deuteron is the result from this one. Again, we combine with proton because on the sun there are a lot of hydrogen nuclei. So hydrogen will combine with deuteron, and it forms the light isotope in helium, which is helium-32, plus the photon or the gamma ray, right? Yes, the mass the energy could be found from the mass difference. You start from the nucleus of hydrogen 1 and the deuteron, right? The bigger version of the hydrogen, and the output is the light version of the helium-32. And you find that the energy for the photon or even the helium-32 will be 5.49 mega electron volts. Okay. In the third process, we could have two ways. The first way is that the proton hydrogen 1 and the light helium-32 combine to form the typical helium, which is helium-42, and we get also positron. And it happens according to this process. Proton and the light version of helium-32, we get helium-42, which is the typical isotope for helium. We get positron, and we get again the photon, okay, the gamma ray. Okay, if you want to find the mass difference, right, and then you combine, you multiply it with 931.5, you get the released energy for these three particles, helium-42, positron, and the photon, and we get 19.284 mega electron volt. Another choice of the third reaction, fusion in on the Sun, two light heliums that unite to form an ordinary helium-42 and two protons. Okay, we start from the light versions, the light isotope, two light isotopes of the helium, which are helium-32, and we get helium-42 and two particles of proton. You could see that here you get number 6, right, and the number A, right, the number of nucleons, and on the right hand side you get also 6, okay, 4 plus 1 plus 1, and what about Z, which is the proton number? You have 2 plus 2, and right here you have 2 plus 1 plus 1, which is also 4. So this equation is balanced, and if you want to find the released energy, just first compute the mass difference and multiply it with 931.5 from the Albert-Einstein energy relation. Okay, once you substitute the mass of the light helium nuclei, you get helium-32, and you get 12.95859, okay, which is the amount of energy. Okay, it's quite high, right? And the above three sequential process is known as proton-proton cycle, which is believed to be the state of energy liberation in the Sun and other stars, which are rich in hydrogen. Okay, they are full of hydrogen nuclei. If you don't completely understand, just take a look at this figure. You have hydrogen nuclei, and they combine together. You get electron neutrino, right? And you get the positron, and now you have deuterium, which is the bigger version of hydrogen. The deuterium combines with the typical hydrogen. You get the photon and the gamma ray, and then you get the light version of helium, which is helium-32. On another side, the same process, okay, take place, and once we have helium-32 will combine together, and we will get some energy, and we get a proton. We get the hydrogen 1 and helium-42, and that's the 3 state, 1, 2, and 3. Okay, 3 state of 1, 2, 3. 3 states of the nuclear fusion that could take place on Earth. All right. I hope that this might not be too difficult for you. All right. If you go further, you could see that as seen from the reaction, the liberated energy is carried primarily by the gamma rays, positron, and neutrinos. Gamma rays are soon absorbed by dense gas, which will raise the temperature. Okay, we will raise the temperature of that gas. The positron combine with electron, and both will produce the gamma rays, which in turn are also absorbed by the gas. Okay, so the temperature on the Sun is extremely high. Okay, yes. What else? Why almost never interacting with the matter? The neutrino Okay, because neutrino is neutral, right? It has no charge. It will not interact with anyone. Okay, that's the property of the neutrino. Of course, it will not have any reaction to any particle, so it will escape from the sun or from that star. And and we would believe that we receive a lot of neutrinos from the sun. All right. Yes. This energy liberating fusion on the sun are called thermonuclear fusion reactions. Okay, we move to the next thing, the net energy release, which can be calculated from the mass balance, turned out to be 26.7 mega electron volt. If the sun were to continue to radiate at the present rate, about 130,000 kilowatt hour, it would take about 75 billion years to exhaust its supply of proton. Okay, in order to consume all proton completely, it would take 75 billion years. So it's 75. รับผมเข้า YouTube โอเคผมก็รอใช้สิทธิ์อยู่นะครับโอเคไม่ค่อยได้เข้าแวะดูนะครับ Alright, I hope that everyone has no problem. Okay, the next thing for two nuclei to fuse. No. The fundamental challenge of nuclear fusion is that they requires nuclei. They require kinetic energy for the nuclei to overcome the repulsive Coulomb force between them at a close distance. For two nuclei to fuse, they must come together within the range of nuclear force, typically on the order of 2 femtometer. At the distance of 2 femtometer, the potential energy of two protons is on the order of 1.1 10 to negative 13 joule, or 0.7 mega electron volts. That's the energy we need to supply to the nuclei. Okay. Yes. Next one. The temperature T for a gas with the average translational kinetic energy. This is from the Boltzmann constant, right? From the typical gas calculation, in order to get that amount of energy in the SI scale, the temperature, this is the Boltzmann constant, 1.38 10 to negative 23, and the unit for that. You need to have the energy T on the order of 5,000 million Kelvin, okay, so that you could supply the kinetic energy to the nuclei at this distance. The temperature must be on the order of millions of Kelvin, so the nuclei can have enough kinetic energy to overcome the electric repulsion, and it can achieve fusion. So the nuclear fusion could not take place on Earth. It's very difficult to take place. So right now we could not build up the the chamber or the experimental site for the nuclear fusion on Earth, because it requires extremely high energy, million Kelvin. Okay, fusion reaction that appear most promising for human is the deuterium-2-1, because we could find deuterium from the sea, and tritium. Tritium is even the heavier isotope of the hydrogen. Reaction sequence is the following. You start from deuterium-2-1, two particles of the deuterium-2-1. You get the light version of helium-3, and you get neutron. Okay, and once you want to find the liberated energy or the releasing energy, you could find the mass difference, and you multiply it with 931. ผมต้องปล่อยคุณเท่าไหร่นะ950ใช่ไหมครับ and you will get you substitute the mass of the deuteron 2 times, because we start from 2 particles of deuteron. The next thing is we are subtracted by the mass of helium-3, the light version of helium, and here is the mass of the neutron, right? In atomic mass unit, if you multiply with 931, you get the liberated energy of 3.27 or 2677 mega electron volts. And the next sequence of this process is that, or the next possible way is that you start from 2 particles of deuterium-2-1, and you get tritium and proton. Okay, that's also a possible case. And in this way, you will find that the mass difference could be also computed, and the released energy will be 4.0315. It's even bigger than the helium-3 version. Let's talk about the released energy in the reaction of helium-3 with deuterium. If you start from helium-3 and deuterium-2-1, and if the result turns out to be helium-4 and nucleus of hydrogen 1 or the proton, what is the release energy then in this case? And of course, we use the typical way in order to find the released energy, and that way is the mass difference, right? The mass difference. So we start from 2 particles here. So we substitute the mass of helium-3, the light isotope of helium, and the heavier isotope of hydrogen, which is deuterium-2-1, the mass of deuterium, and we subtracted by the mass of the output, which is helium-4 and the mass of the proton or mass of hydrogen 1. And it turns out that the released energy becomes 18.352 mega electron volt, which is quite high. Okay, if we can really build up this nuclear fusion. Okay, what we can do is only the calculation from theory, how much energy we could get, right? And you could see that the released energy is quite high, but from the uranium-235, you get somehow 200 mega electron volt, right? But this one is 18.352 mega electron volt. All particles in nature are subject to 4 fundamental. Now we finished the nuclear fusion, and we will move to particle physics as same as M605. All particles in nature are subject to 4 fundamental. Before we go to particle physics, we will talk about 4 fundamental forces, because the forces could be explained by the meditation or the exchange of some particles. Okay, so it has some relation to the particles in physics. Okay, so if we make a conclusion, you could see that every force in physics could be classified into these four types, which are strong force, electromagnetic force, weak force. This force may not so widespread or may not easily heard before, right? Weak force and gravitational force. Of course, you may have already seen gravitational force, which is the G, right? The G, which is the gravitational acceleration on Earth, and if you multiply it by mass of anything, you get the force, right? Okay. Let's move to the next thing. Here are four fundamental forces, and each force could be explained by particles. Okay, let's see the details of each force. Okay, let's start from the strong force. Strong force is the greatest force in all these four categories. Strong force is responsible for the tight binding of quarks, okay, to form the neutrons, okay, to form the protons. It's also responsible for nuclei, okay. If you want to let neutron and proton to stay together, and that's the task for the nuclear force. Nuclear force is a member of a strong force, okay, and the strong force represents the glue, okay, that holds the nucleon to stay together, and it is the strongest of all four fundamental forces. The strong force is a very short-range force. If we are far away than 1 femtometer or on the scale of femtometer, the strong force will not exist. Okay, it exists only in the scale of femtometer, 10 raised to negative 15 meter. Let's talk about the electromagnetic wave that we have seen in the last semester that has E field and M field, which is magnetic field. Magnetic force is about 1 by 100 times. Okay, it's less stronger. It's 100 weaker than the strong force. Okay, and it is responsible for the binding of atoms and molecules. Okay, if you want to join two atoms together, okay, they're gonna have the covalent bond and so on. They have to share electron. Okay, and yeah, that's the bigger scale than the strong force inside the nuclei. The electromagnetic force is the long-range force. Okay, if you transmit the electromagnetic wave for several kilometers, you still get the signal, right? For example, the signal in your mobile phone, the signal for your television is transmitted from the station, which is quite far away from us. So the electromagnetic force is a long-range force that decreases in strength as the inverse square. So if we are far and far away from the source, we will get weaker energy or the signal of the electromagnetic source, right? And the weak force, right, is the third one, is a short-range force. It's a short-range nuclear force that it exhibits in the instability of certain nuclei. The weak force is involved in the mechanism of beta decay. Its strength is 1 million weaker than the strong force. Let's talk about the fourth force, which is the gravitational force. The gravitational force is a long-range force. You could get the gravitational force from the sun, but it's not strong. Okay, the strength of the gravitational force is about 10 to negative 43 times that of the strong force. Is very, very weak here. Although this familiar interaction is the force that holds the planets, star, and galaxy. Okay, the planet, the star, the galaxy stay together by due to the gravitational force. Its effects on elementary particles is negligible, so we would neglect the strong force. The gravitational force to the elementary particles. The gravitational force is by far the weakest force of all four fundamental forces. And modern physics often describe the force between particles in terms of interaction, in terms of action of field particles, or it's easily known as quanta, which is the plural form of quantum. Forces between two particles are conveyed by the exchange of field quanta. This process is similar to the covalent bond between two atoms created by an exchange or sharing atoms. Okay, so when you exchange the particles, so you have the force to each other. That's the meaning of this sentence. And in chemistry, in the bigger scale than us, they have the covalent bond, right? And that in that bond, the atom just share the electron, right? So we arrive at the summarization, summary of four fundamental forces. There are four forces, right? Gravitational force, electromagnetic force, weak force, and strong force, right? Relative force, right? If we say strong force is the greatest amount, so we would say that this is this has value of 1, right? So it's unified. It's scaled to be number 1. So the other, which is weaker, should be less than 1. For example, gravitational force, it is around 10 to negative 43 to 10 to negative 38. Okay, and electromagnetic force is 100 weaker than the strong force. The weak force is not so much weaker. It's weaker than electromagnetic force. It's around 1 million or 1 million, 10 million weaker than the strong force. The range of these four forces will take place. The gravitational force will have the range of infinity, and the force decreases with the distance square. Electromagnetic force too. We can get electromagnetic forces in infinite distance, and the strength will decrease with the distance square. Okay, the weak force is given by 10 to negative 18. Okay, this is the distance in meter, so it's even less than 1 femtometer. It's 1 by 1,000 femtometer. It's very, very short. And for the strong force, we are on the order of 1 femtometer, okay, or less than that. The type of the force, whether it's repulsive or attractive. Gravitational force is attractive, right? Because if you jump onto the air, okay, the earth will bring you back to the ground, right? And that's the attractive force. Electromagnetic wave electromagnetic force could be either repulsive or attractive force. And the weak force can be also either repulsive or attractive force. The strong force can be either repulsive or attractive force. Okay, both. And carrier particle, what is the carrier particle of gravitational force? It is expected to be graviton. Okay, graviton is not yet discovered. Okay, electromagnetic force, what is the particle that carries this force? It is photon. Okay, photon doesn't include only the light, but also any frequency of electromagnetic wave. And weak force, what is that? What is the carrier particle? The carrier particle of weak force is the carrier particles of the weak force are W plus boson, W minus boson, or Z0 boson. And what about the carrier particles for the strong force? It's expected to be gluon. Okay, from the word glue. Okay, so what is the status right now? How human has discovered the carrier particle? The carrier particles for the gravitational force is graviton, but graviton is conjectured. Okay, it's not yet found in experiment, but it is predicted to exist. What about photon? Photon is already found in experiment. What about weak force? What about W plus boson, W minus boson, or Z0 boson? Well, all these three particles have already found in experiment. What about the gluon, which is the carrier particle for the strong force? Gluon is not yet found for human. Gluon is not yet found by human. It is expected to exist. Okay, so it's conjectured. Yeah, that's the status right now. Maybe in your generation, maybe I have passed it away. All these two things may have been found in laboratory or in experiments already. Okay, it could take place. Let's talk about quarks and other particles. Quarks, leptons, and the particles that convey forces. What is lepton? Lepton, for example, the electron. Okay, electron is an example of lepton. The particle that convey force, for example, photon, are now thought to be the truly fundamental particles. Before we go to the full table of elementary particles, let's talk about direct theory. For every particle, there is an antiparticle, right? As you know, electron has its antiparticle, which is positron, right? And the antiparticle would have the same mass as that particle, but in the opposite charge. Not only the opposite charge, but also the opposite number of something. An antiparticle is usually designated by a bar over the symbol. For the particle, for example, except for the positron. Positron doesn't have bar above. We just replace the negative here on electron to be plus. Okay. It depends on the people who want to write down. Among the exceptions are the photon and neutron pion, denoted by pi 0, which are their own antiparticles. They don't have antiparticles, they are already their own antiparticles. Okay, photon and neutron pion. You see pion later. When a particle meets its antiparticle, both particles will be annihilated. And the annihilation will give you high energy photons or gamma, right? It is useful to classify particles in terms of their interaction. We will distinguish also between boson and fermion, right? Boson always have zero or integer spin, while fermions have half integer spin, right? 1/2 or 3/2. That's the fermions. Fermions obey the exclusion principle, and boson do not. What does that mean? It means fermions could not take place or stay at the same location and at the same time. But if you talk about that in terms of quantum theory, the fermion cannot have the same quantum number, same quantum state at the same time. So they cannot stay at any location together at the same time. That's the Pauli exclusion principle. But boson could stay together, but boson will follow the property or property theory by Boser. Okay, we arrive at the standard model of elementary particle. Here we have fermion on the left, right? Fermion is right here, and boson is right here on the right. Okay. So what happened? And as you see, here is the typical particles, right? On these three columns. And these three columns, you get antiparticles, right? For example, the up quark. Let me introduce again. Here is fermion, and here are bosons, right? The fermion could be classified into two categories. The first one is quarks, and the second one is leptons. Quarks will be the one that's related to a strong interaction, but this one will be related to the weak interaction. Okay, let's talk about quarks. The smallest one for the quark is the up quark and down quark. The mass of the up quark is 2.2 mega electron volt per c square, and the charge will be half integer, right? The charge will be 2/3 of electron charge, and down quark is more massive, is 4.7, and charge is negative. Okay, and the spin number is 1/1/2. That's the half integer spin number for the fermion. But the gluon could have spin number as number 1 or 0. That's different. Okay. The up quark, the up quark had its own antiparticle, which is known as anti-up. The anti-up has the same mass as the up quark, but the charge is different. 2/3. This one is negative 2/3. Okay, and now we go to the bigger version of quark, which is charm quark, and charm quark and straight quark. Okay, it's on the order of 1.28 giga electron volt per c square, and this one is 96 mega electron volt per c square. Both will have their own antiparticles with the same mass, but the charge will be opposite, right? If this one is positive, the antiparticle will be negative. If this one is negative, the antiparticle will be positive. Okay, with the same mass and spin number. So let's talk about the bigger quark, and they are top quark and bottom quark. You could see the mass here is 4.18 and 137. It is very, very big. And the top quark and the bottom quark have their own antiparticles with the same mass and the opposite charge value, the same spin numbers, 1/2, right? The big quark are not so stable. Okay, they're gonna decay to the smaller quarks. And let's talk about leptons. The one that is very well known to us is electron. Right? Electron has a mass of 0.511 megaelectron volt per c square. But of course, the charge for electron is -1 because its electron is negative, and we use the charge of electron to be the reference, right? So yeah, it's -1. Spin number for electron is 1/2. Okay, and that's a negative one. The bigger version of electron is muon. Okay, muon is actually the bigger electron. It has the mass of 105. Okay, 200 times 200 more massive than the electron. But muon will not be so stable. They're gonna it's gonna decay to electron later. But the people have discovered this bigger particle because they use the particle accelerator. You know particle accelerator, right? ทุกคนรู้จักเครื่องเร่งอนุภาคใช่ไหมทุกคนรู้จักเครื่องเร่งอนุภาคไหม particle accelerator เป็น if you wanna, but it's not difficult to predict it. There might be bigger quarks or leptons if you have the bigger or better particle accelerator. And the place you can study something or discover something about elementary particles is in SAT. Oh no. It's in sand. Okay, I may not say properly. It's in CERN. You can say it's CERN, right? In English, CERN. CERN came from the French word, right? Council European Polar Researcher Nuclei. Okay, this is French. I don't know how to pronounce in French, but yeah, this thing. Okay, I would not pronounce it correctly. I have never studied French. Okay, and if you want to discover new or bigger particle, you should go to SAN or to CERN. Okay, if you translate it in English, it's going to be European Council for Nuclear Research. Okay, and there the people are studying something about elementary particles like quark, leptons, and so on. If you want to see the image of sand is somehow like this. Okay, you just do the PhD. If you fall in love with particle physics, you just do the PhD and try to be very, very good, okay, and apply for the job in CERN or in SAN. They will let you work there, and you might be the person, or you might be the physicist who discovered the new particle, okay, and they might use your name, your surname, as the name of that particle. Okay, where is SAN or CERN? อันนี้ นอกเรื่องแต่ว่าเล่าให้ฟังนะครับว่ามันเป็นยังไงครับ here okay sand or CERN is in yeah sand or CERN is in Switzerland, but it's very close to the border between here is France, here is Switzerland, and here is the line of the border between those two countries. And sand or CERN located in this area, okay, very close to the border, which is this figure. Okay. This one, okay, this one located here, and yes, and the particle accelerator would be somehow this, okay. Yes, if you work there, okay, here you will need to have so many steps in order to accelerate the particle, okay, and they build up the particle accelerator under the ground, okay. It's not the same as no, it's not a figure of it's not a figure of particle accelerator actually. Here, okay, they have their own factory, and yeah, here is the tunnel or the pipe, okay. The particle will be accelerated through this tunnel, okay, and you could see that the particle accelerator tunnel is built up underground. It's like the train which lies under the ground, okay, but it's not the route for a train, it is the route for particle accelerator. What is the reason why they build up the particle accelerator under the ground? Because if you build up on the ground, it might be difficult to control, and someone may disturb them, right? And you need a lot of space and so on. And yeah, if you build up under the ground, you don't have to worry that your tunnel will disturb anybody, okay. And that's the reason. For the particle accelerator in the United States, I think it's in the California. Okay, particle accelerator in the United States. Yeah, they build up above the ground. Okay, for example, you could see here. Here, it's like they build up in a circular like way, right here. They let the particle be accelerated in this way. Okay, once the particle is accelerated, they would have high kinetic energy, right? And when it hit the nucleus, you could see some new particles, okay, like this. They build up on Earth. It's not like sand in the Switzerland and France. They build up the tunnel, the particle acceleration inside the tunnel under the ground. And what else? here is inside the particle accelerator. Okay, you use electromagnetic to accelerate the particle. And what else? There's nothing more, right? Here in sand. Okay, they build up under the ground. Okay, if you want to discover new particle, you have to do the PhD in physics and apply for the job in CERN or sand. All right, and you have to live in Switzerland or in France. Okay, and in your life, you could explore, you could discover. Okay, you could discover new, bigger particles apart from top quark, bottom quark, tau, lepton, or the neutrino. Okay, there are still many open questions in physics, actually. Okay, let's talk about our story. Electron, okay, has the mass of -1, -1. The tau is bigger version of electron of muon, and tau will decay to muon, and muon will decay to electron because they are not stable. But the people could discover all these two things because they used the particle accelerator like this. Okay, you accelerate some particles to hit something. Okay, it's like in several kilometers. Okay, 10 kilometers, something like that. Okay, and you will get really high kinetic energy of the particles. And once that particle hit the nucleus of something, you will finally receive new effects. Okay, but you need anyway the particle accelerator. Okay, that's the the leading unit on Earth. Okay, I don't know whether there is particle accelerator in Thailand or in Australia. Okay, the antiparticle of electron is the positron here. Okay, usually E minus or E negative, and here is E plus. You could see the same mass of electron for positron. The charge is no longer -1, it's rather +1. The spin number is the same, 1/2. Okay, and the antiparticle for the muon is known as, it's called anti-muon. The mass is the same as muon. The charge is +1, it's +1 rather than -1. The tau lepton has also the antiparticle, which is known as anti-tau, with the same mass 1.7768 giga-electron volts นะครับผมก็อายุแก่เกินแล้วนะครับไม่ได้เรียนฟิสิกส์มาไม่มีโอกาสค้นพบพาร์ติเคิลอนุภาคใหม่แล้วนะครับต้องเป็นรุ่นคุณแล้วนะครับเขียนว่าanti-tau, right? These leptons has the negative charge, right, or even the positive charge with the antiparticle version. For the corresponding lepton that has no charge at all, and those are called neutrino. Electron has its own neutrino, which is electron neutrino denoted by nu with subscript e. The charge is 0 and spin number is the same as electron 1/2, the same as quark 2. The mass is very small. Right now we don't know exact value for electron neutrino mass. Okay, the mass of electron neutrino is still an open question. What is that? But it's very hard to determine the mass of electron neutrino because electron neutrino will never interact to any other stuff because they have no charge. Okay, unlike alpha particle or proton or something like that, they have charge, so we can detect them easily. But electron neutrino is neutral; it has no charge, so we could not measure the mass of this thing easily. Okay, the bigger version of electron neutrino is muon neutrino, which corresponds to muon. Okay, the tau has also its own neutrino, which is known as tau neutrino. And all these three neutrino has its own antiparticles, which are called electron antineutrino, denoted by bar above the letter nu. Okay, and muon neutrino has also its own antiparticle, which is known as muon antineutrino. Tau neutrino has also its own antiparticle, which is called tau antineutrino with the same mass. And please note that the value of the charge here is 0, right? Because neutrino has no charge. So there is no difference at all between antiparticle or the original particle because it has no charge. So what is the classification of the neutrino then? The same spin number you can see here 1 by 2, 1 half, right? The charge is 0. Unlike electron or muon and tau, they have -1 charge. An antiparticle has 1 charge. But neutrino has 0 charge, and the antiparticles have also 0 charge. So what is the difference? The mass are the same here, okay, for all these three particles. I would say the difference for these two groups, the neutrino and antineutrinos, is that the lepton number, okay, the typical lepton would have lepton number as number 1, but the antiparticle will have lepton number as -1. Okay, it's not charged. Okay, we will see something about the lepton number later, and now we move to boson. Boson is the particle that interact to carry electromagnetic force, or even the strong force or the weak force. Okay, and they have spin number as 1 or 0. Okay, the bosons that have spin number as 1 is called vector boson. And if the spin number of the boson is 0, we call scalar boson, okay, which is Higgs here. Okay, Higgs boson. You know why we call this one as Higgs? Because Professor Higgs, Higgs is the surname by him. Okay, is his surname. Professor Higgs has predicted this one, and he predicted since he was quite young until now. He is 70 years old or something like that. He didn't, as I know, he didn't pass away yesterday, Professor Higgs. And you know, Higgs boson has been confirmed I think in 5 years ago or 10 years ago. And the place that discovered Higgs boson, do you expect? Could you guess where the Higgs boson has been confirmed? คุณคิดว่า Higgs boson ค้นพบที่ไหนก็คือมันถูกคาดการณ์ว่ามันจะต้องมีน่ะ particle แบบนี้นะครับแล้วคนนั้นน่ะก็ชื่อ Higgs นะครับแต่ก็ยังไม่มีใครทำการทดลองยืนยันได้ว่า Higgs เนี่ยมันมีจริงๆหรือว่าไอ้โบซอนตัวเนี้ยมีจริงเมื่อ10 ปีหรือ5 ปีที่แล้วเนี่ยนะครับค้นพบแล้วนะครับสถานที่นั้นก็คือที่แสนนั่นแหละครับโอเคไหมถ้าคุณอยากค้นพบอะไรใหม่ๆนะครับไปเรียนเลยนะครับโอเคไหมไปทำงานอยู่ที่แซนครับโอเคyes here is gluon. Gluon is expected to exist, is not confirmed yet. It will interact in the strong force. Photon is already confirmed to exist. Okay, we could find photon, and is the interacting particle in electromagnetic force. Z0 boson has no charge at all. W plus boson has 1 plus charge as same as electron, and W minus boson will have negative 1 charge. Okay, they're the same as electron, but the spin number here is different. It's number 1, and the mass is quite big. Okay, the mass is on the order. The mass of boson here, Z0 boson, W plus boson, W minus boson are on the order of giga electron volt per c square. The mass of photon is 0. It has no mass. Gluon also has no mass, and the Higgs boson is even heavier. It's 124.97 giga electron volts. Okay, and that's the whole thing about standard elementary particles. If you want to see the size of something, this is what we have considered in the previous chapter. That's the atomic model, right? There are many orbits for electron, and the size of electron is 10 raised to negative 18. Okay, and atom is on the order of 10 to negative 10, which is 1 angstrom, right? Or you can say also in nanometer it is 0.1 nanometer. And inside the atom we have the so-called nucleus, but this one is written in German. It's pronounced as can, right? It's known as can, but this is the nucleus. It's full of nucleon with a proton and neutron. And inside the proton or inside the nucleus, whether it's proton or neutron, we have some particle inside. Okay, the size of the nucleus is around 10 to negative 14, 0.1. No. 10 femtometer. Okay, to 6 femtometer. And the size of the proton is 1 femtometer, and the size of the quark will be the same as electron, which is 10 to negative 18, 1 by 1000 femtometer. Okay, the property of the quarks and the property of the quarks could be summarized as this table. Up quark, down quark, strain quark, sham quark, bottom quark, top quark, right? They have charge, which is divided by the charge of electron as 2/3, negative 1/3, negative 1/3, 2/3, negative 1/3, and 2/3, right? The spin number of all quarks is 1/2. And the baryon number, this might not be well known to you. We will talk about baryon number later. It's 1/3, 1/3, 1/3 for everything. The straightness is negative 1 for the straight particle. The charm nets for charm quark is +1. For the less are 0. Okay, the less have 0 charm number. The less has 0 straightness. Regarding the bottomness, only the bottom quark has +1 value. The rest have 0 bottomness. Regarding the topness, only the top quark has +1. The rest has 0 topness. Okay, and we arrive at this time and you could take a break, right? So see you on next Wednesday. Right. Okay. See you next week. Homework I will assign to you later. The calculation of the released energy in nuclear fusion. Okay. If you have any questions, just let me know. If not, then we're gonna quit the lecture right now. see you on next Wednesday บ๊ายบายครับสวัสดีครับ
ดียวงง
เคก่อนมาแล้วนะครับ1 คนนะครับผมไม่เข้าใจว่าทำไม สตรีมแลบไม่ออกนะครับโอเคก็สำหรับห้อง605นะครับสำหรับห้อง605 เราจะเรียนกันเฉพาะ คาบ3นี้เท่านั้นนะครับส่วนคาบที่4อาจารย์ณัฐพงศ์นะครับเขาขอเข้าแทนนะครับ เขาขอเข้าแทนชดเชยคืนของเขานะครับโอเคไหม หวังว่าคุณไม่มีปัญหาใดๆครับหวังมันเซตเป็น private เหรอมิหน้าหาไม่เจอนะครับ not private public ไม่รู้ทำไงครับ entertainment โอเคนะครับขอแจ้งอีกรอบนะครับ M605 นะครับห้อง605เราจะเรียนการเฉพาะคาบ3นี้เท่านั้นครับมีกรพิมพ์ชื่อมา1 คนนะครับโอเค shown as private micro โอเค605นะครับไม่รู้ว่าเข้ามากันแล้วหรือยังครับเราจะเรียนการเฉพาะคาบ3นะครับหมายถึงว่าถึงเท่าไหร่ถึง11ก็จะถึง50นะครับโอเคไหมให้คุณเบรก10 นาทีนะครับก็จะมีเบรก10 นาทีถึงแค่50นะครับแล้วเราก็จะเลิกเพราะว่าอาจารย์ณัฐพงศ์นะครับที่เขาขอคืนนะครับเนื่องจากว่าเขาเกิดอุบัติเหตุครับที่ผมมาชดเชยนะครับเขาจะขอคืนตรงนั้นนะครับคุณก็กลับไปที่ห้องเรียนของเขานะครับในคาบที่4นะครับโอเคไหม alright I hope that everyone could understand right okayเข้ามากันแล้วหรือยังครับ All right. Do you understand that?โอเคมีคนที่อยู่ที่ OBS บ้างแล้วนะครับผมขอบอกห้อง605นะครับว่าเขาจะมีการชดเชยนะครับในคาบที่4นะครับ M605 your mathematics teacher is going to take the fourth 4 hours. Okay, please go to his please go to his classroom, online classroom after this classroom. Okay, ห้อง605นะครับโปรดไปที่ห้องเรียนของอาจารย์ณัฐพงศ์นะครับเนื่องจากว่าเขาจะขอชดเชยนะครับในวันครับในวันนี้นะครับโอเคก็สิ่งที่จะแจ้งให้คุณทราบก็จะประมาณนั้นโอเคalright โอเคนะครับปฏิหารนะครับบอกเพื่อนด้วยนะครับว่าหมดคาบนี้นะครับหมายถึง10-50เนี่ยนะครับก็ให้คุณไปเรียนวิชาคณิตศาสตร์เพราะว่าอาจารย์ณัฐพงศ์สอนคณิตศาสตร์ที่ผ ผมเคยไปใช้เวลาเขานะครับเขาขอคืนนะครับ okay now it's time for us to M605. Let's continue our story. นะครับผมก็จะปล่อยคุณประมาณ10-50นะครับเนื่องจากว่าเขาเรียกว่าไงเนื่องจากว่าปล่อยให้คุณเบรก10 นาทีเพื่อว่าจะได้เผื่อเวลาเข้าเรียนวิชาใหม่ครับ Nuclear fusion, particle physics, already. Okay, one thing that I have added is the equation of muon decay, right? This is muon minus. We're gonna have electron and is that correct? Yes. Muon minus will decay into electron, and the neutrino for the muon and the antineutrino for the electron. For the muon plus, which is the antiparticle of the muon, a typical muon, will decay into positron นะครับ605นะครับใครที่มาใหม่นะครับวันนี้หลังจากจบคาบนี้แล้วนะครับที่10:50นะครับให้คุณเตรียมไปเข้าเรียนคลาสเรียนของอาจารย์ณัฐพงศ์นะครับโอเคไหมให้คุณไปเข้าเรียนที่คลาสรูมของอาจารย์ณัฐพงศ์ที่สอนแมทผมจำไม่ได้รหัสของคุณครับที่เขาป่วยอะไรนั่นครับโอเคไหมคุณที่เขาเกิดอุบัติเหตุครับโอเคไหมโอเคplease go there. Okay, let's talk about our story. The muon plus, which is the antiparticle of the muon minus, will decay into positron. Okay, we start from the positive, and we will have the antineutrino for the muon, and here is the electron neutrino. Okay, now we move to the law of conservation. You have seen the lepton number, right? Lepton number for electron is 1. Lepton number for positron will be -1. And the lepton number, this is the electron lepton number, and here is the muon lepton number. Electron and positron have no muon lepton number. Electron and positron have no tau lepton number, 0 here. Okay. There are 3 conservation laws in which is related to lepton numbers, because we have 3 lepton numbers, right? Electron lepton number, muon lepton number, tau lepton number, right? The electron neutrino, this one, has electron lepton number as +1. The electron antineutrino, nu by with subscript e, will have the electron lepton number as -1. Okay, and both will have muon lepton number as 0. both will have tau lepton number 0. Okay, what about muon? Muon with negative charge here, with negative charge, would have muon negative and muon positive, which is the anti-muon, would have 0 electron lepton number. And for the muon lepton number, it's different. Both are different. The muon will have muon lepton number as +1. The anti-muon or muon plus will have muon lepton number as -1. And the tau lepton number, both will have 0 tau lepton number. Okay. And regarding the neutrino, muon neutrino, which is denoted by nu with subscript mu, or even nu bar with subscript mu, would have 0 electron lepton number, and for muon lepton number, both are different. The typical muon lepton number would have muon lepton number as +1. The muon antineutrino, this one with bar, would have the muon lepton number as -1. The both will have 0 tau lepton number. And when we move to tau with negative is the typical tau, is the original tau lepton. Tau lepton and anti-tau would have 0 electron lepton number and 0 muon lepton number, because it both have nothing to do with muon and electron. But for the tau lepton number, both are different. The typical tau lepton would have +1 tau lepton number. The anti-tau or tau plus would have -1 tau lepton number. When we talk about the tau neutrino นะครับสำหรับ605ที่เข้ามาใหม่นะผมจะค่อยๆชี้แจงนะครับว่าเขาให้คุณไปเข้าห้องเรียนวิชาคณิตศาสตร์ของอาจารย์ณัฐพงศ์นะครับเขาจะขอชดเชยในคาบที่4นะครับหลังจาก 10:50 นี้ไปนะครับโอเค and yeah the tau neutrino the tau neutrino and tau antineutrino both will have 0 electron lepton number. Both will have 0 muon lepton number. But for the tau lepton number, both are different. The tau neutrino would have the tau lepton number as +1. And the tau antineutrino would have the tau lepton number as -1. Okay. Please note that all the neutrinos are stable, also electron. Okay. The bigger electron like muon and tau are unstable. And there are 3 conservation laws according to lepton numbers. Because we have 3 lepton numbers, there will be 3 conservation laws. The first law is law of conservation of electron lepton number. The second one is the law of the conservation of muon lepton number. The third one is the law of conservation of tau lepton number. So all of these, okay, would have their own conservation laws. Let's see what is that. The law of conservation of electron lepton number states that the sum of the electron lepton numbers before a reaction or decay must equal the sum of the electron lepton numbers after. Okay, before and after should remain the same number of electron lepton numbers. Okay, or after the reaction or the decay. The electron and the electron neutrino are assigned as a positive electron lepton number Le equal to 1. Okay, the straightforward neutrino. The anti-leptons like positron and electron anti-neutrino are assigned to have the electron-lepton number as sorry, this is negative 1. Sorry for that ผมพิมพ์ผิดนะครับตรงนี้ต้องลบ1นะ My God, this is negative 1. Okay, and all particles apart from this would have electron-lepton number as 0. Okay, only electron and electron neutrino would have +1 electron-lepton number, and proton and electron antineutrino would have electron-lepton number as negative 1. Okay. And for example, if you consider the neutron decay, right? Before that, we have seen neutron that decay to be let's okay, no. Let's say we consider beta decay. Here. Okay. This is not correct, right? It's the wrong question. Here is correct. Neutron inside the nucleus will change itself to become proton when there are too many neutrons in that nucleus, and what we get will be electron, okay, moving from the nucleus. And we also have the electron antineutrino, this one. And here is the process of neutron decay. Okay, when the nucleus has too many neutrons, or the nucleus is neutron rich. Okay, neutron rich. So we are gonna use the consider this one in beta decay. In beta decay, you will see that N is decomposed. N on neutron, it is decomposed into proton, right? This one, and electron, right? And electron antineutrino, right? This one. Let's check the electron-lepton number. If you check the electron-lepton number, I don't know which page. Here. Okay. If you go back to the table, to this figure 31, which provide the electron-lepton number, right? Neutron has 0 electron-lepton number, right? So we have 0. And proton has nothing to do with this because proton is baryon. It has 0 electron-lepton number. Okay, any particle apart from electron and electron neutrino, positron and electron antineutrino would have some value for electron-lepton number. The rest will not have electron-lepton number at all. Proton also doesn't have any value for lepton number 0 here. Electron here. Electron would have plus 1 lepton number, so we write down here plus 1. Electron antineutrino would have negative 1 for lepton number, so we write down negative 1. And you can see that the left hand side remains 0 and the right hand side will also remain 0. So we get actually the balance of this equation. We get 0 equals 0. So once we get the conservation, you could see that the total number of lepton number on the left before the reaction or the decay is 0. And the total number of lepton number after the decay will remain also 0. Both are equal to each other. So the lepton number is conserved in this process, in this decay. So this decay could take place in nature. That's the meaning of lepton number. Okay, you understand that? There will be conservation of lepton number, conservation of muon lepton number, conservation of tau lepton number too. Okay, now we move to to this one. Determine which of the following decay schemes can occur on the basis of the conservation of lepton number. So, I'm not sure whether this process is correct or not. Muon decays into electron antineutrino, and muon neutrino. Is this valid? Is this correct? Is the conservation of the lepton number valid for this equation? That's the question of this example. And let's consider the second decay or the second reaction. This is pion. Okay, pion plus. Pion has 3 different types: pion 0, pion minus, and pion plus. Here is pion plus, and pion plus is decomposed into muon or anti-muon. Actually, muon plus is the anti-muon, the antiparticle for muon here. Pi plus is decomposed or decays into anti-muon, and what we have will be muon neutrino and electron antineutrino. I'm not sure whether I have written the correct yeah, already correct. Okay, yeah, this one is already correct. I'm afraid that there would be typo, wrong typing in this one, but it's not. Okay, the decays in 114, okay, in both equations have something to do with electron and muon, right? The outcome are expressed in terms of electron and muon. So if you go back, there will be 3 conservation laws, right? For electron lepton number, muon lepton number, and tau lepton number. Because we don't have tau lepton at all in these 2 equations, so we are going to use only 2 conservation laws, and that are for electron lepton number and muon lepton number. Okay? Okay. Yes, let's consider the both electron-lepton number and muon-lepton number need to be conserved. In the first one, 114A, this one. In 114A, we consider only this equation, but for both lepton numbers, the first one is electron-lepton number, and the second one is the muon-lepton number. For electron-lepton number, you could see that muon has nothing. Muon here. Muon has 0 electron-lepton number, so we write down on the left 0 electron. When we talk about electron-lepton number, electron has 1 electron-lepton number, so we write down here 1. Our next particle is electron antineutrino. Because this is the antiparticle, it's going to have -1 right here. It's going to have -1 electron-lepton number, so we write down -1. The last one is muon neutrino. Because we are considering the electron-lepton number, muon neutrino has 0 electron-lepton number, so we write down 0. And let's check whether this one is correct or not. Yes, 0 on the before the decay, and after the decay we have 0 too, right? 0 as well. So it means that the electron-lepton number is conserved for this reaction or for this decay, but it's not complete. Okay, we have to also consider the muon-lepton number because the whole equation involves also muon-lepton. Okay, muon at the beginning. What is the muon-lepton number? Muon here has +1 muon-lepton number, so we write down 1 for muon. The next one is electron. Electron has 0 muon-lepton number, so we write down 0 on the right hand side. The next one is electron antineutrino. Electron antineutrino has 0 muon-lepton number, so we write down 0. And the last particle, muon neutrino. Muon neutrino is right here. Muon neutrino has +1 muon-lepton number, so we write down number 1 here. And let's consider whether this equation is valid or not. Of course, before the decay we have 1, and after the decay we have 0, 0 plus 1. It turns out again to be 1. So this equation is valid. When this equation is valid, it means the muon-lepton number is conserved. Okay, there is conservation of muon-lepton number. Once we have considered both for this single reaction or decay, we consider both the electron-lepton number and the muon-lepton number. Once both are valid, we will conclude that this reaction or this decay could take place in nature. Okay, could happen in nature because there are conservations for electron-lepton number and muon-lepton number. Let's move to the second reaction or second decay. Proton plus decays into anti-muon and muon antineutrino and electron neutrino. Right. Now, Proton. Proton is not listed in this table, in this figure, but we could easily see Proton has 0 electron-lepton number. Okay, if you don't believe me, you just go to the end of this chapter. Proton Where is that? P-on plus here. P-on plus has 0 electron-lepton number. This is baryon number. We will talk about that later. P-on plus has 0 electron-lepton number. P-on plus has 0 muon-lepton number too. So for this equation, for this reaction or decay, P-on plus would be 0 for both cases. Okay, 0, 0 for electron-lepton number and muon-lepton number. Okay, that's fair. And for the anti-muon, we could also say here, but it's no problem. Let's take a look at this table. The electron, the muon, anti-muon, this one, the antiparticle, would have 0 electron-lepton number, so we write down 0. Muon neutrino, where is that? Here, would have 0 electron-lepton number, so we write down here 0. And the last one, electron neutrino, this one has plus 1 electron-lepton number, so we write down 1. Oh, no, 1 here. Okay, 1. And let's see whether this equation is valid or not. You could see that there is 0 on the left, and on the right hand side we have 0, 0 plus 1, which becomes 1, right? 0 will not be equal to 1. So 0 is unequal to 1. So there is no conservation of electron-lepton number to this reaction or this decay. Okay, we would simply say that this reaction or this decay would never take place in nature. Okay, and if you want to see the muon-lepton numbers, we can go ahead. For pi plus, we have 0 for that, and the anti-muon, which is this one, would have minus 1 muon-lepton number, minus 1, right? Muon-lepton number. And second one, muon neutrino would have 1 muon-lepton number, so we write down 1. And the last one is electron neutrino. Electron neutrino would have 0 muon-lepton number here, so we write down 0. And let's check whether this equation is valid or not. You can see the 0 at the left hand side, and on the right hand side we have minus 1, plus 1, and 0. So it turns out to be 0. So 0 equal to 0 would be perfect, right? It would be all right. But together with the electron-lepton number, the whole process here would not take place in nature, would not occur in nature, because there is no conservation for the electron-lepton number. Okay, and this is the technique we could use to we could use to judge whether any reaction will take place in nature or not. Okay, ก็6.5 จบไว้เพียงเท่านี้ก่อนนะครับให้คุณได้เข้าเรียนอันถัดไปนะครับ M605 ไม่มีการบ้านนะครับของคุณนะครับมี 604 นะครับโอ้604จะมีการบ้านเพราะเขาถึงพวกฟิวชั่นเพิ่งจบฟิวชั่นมาตามคุณมาอยู่นะครับโอเค see you on next Wednesday โอเคครับบ๊ายบายครับสวัสดีครับลืมบอกนะครับ605นะครับให้เข้าเรียนห้องเรียนชดเชยนะครับของอาจารย์ณัฐพงศ์นะครับวิชาคณิตศาสตร์นะครับเขาขอชดเชยวันนี้นะครับมีใครจะเข้าวันที่ซูมไหมเอ่ยไม่มีนะ อันนี้ด้วยเขาวัดปีละทัศน์เขาวัดปีละทัศน์นี่ซูม where's number 2 this is okayอ้าวแล้ววิพจน์มาครับ